You are lying somewhere very still, and above you, without you having to do anything at all, the night has opened itself completely. Let your shoulders soften into whatever is beneath you. Let your breath slow, just slightly, the way it does when you already know you are safe. Tonight we are not going anywhere loud. We are going somewhere quiet and very far and very old. Picture a small moon, pale as bone, circling a giant planet in the outer dark. Its surface is cracked ice, veined with faint lines of reddish-brown, like the crazing on an old porcelain cup that has been dropped once, gently, and kept anyway. Beneath that ice, hidden from every telescope for most of human history, there is an ocean. It has been there, dark and salty and slowly moving, for longer than there have been humans to wonder about it. And every so often, through cracks in that ice, this small moon breathes. Plumes of water vapor rise hundreds of miles into space, catching sunlight, falling back down as snow. A spacecraft once flew directly through one of those plumes and tasted it and found things inside that ocean spray that on Earth we only ever find near life. We do not know even now whether anything living moves in that hidden sea, but for the first time in the history of our species, the question is no longer only philosophical. It is a question we can actually go and answer. Tonight we are going to walk slowly through the most convincing evidence for life beyond Earth that has ever been gathered, not as a list of facts but as a story. The story of everything that has made scientists pause, lean forward and say quietly, "That does not look like nothing." We will drift past ancient meteorites and hidden oceans, past the clouds of a planet so hot it should hold no secrets, and out to a small world circling a star 40 light-years away, where astronomers recently found a gas that, here at least, only life seems to make. We do not need to reach a conclusion tonight. We only need to travel there together, slowly, and let the universe show us what it has been quietly keeping. Somewhere out there, in the dark between worlds, something extraordinary may already be waiting to be understood. Let's go and find it gently, one small piece of evidence at a time. Before we can recognize evidence of life somewhere else, we have to sit for a moment with a strange and humbling truth. We do not have a complete definition of what life actually is. We have a working description, gathered slowly over centuries of biology, chemistry, and quiet observation. Life, as we understand it, takes in energy from its surroundings and uses that energy to maintain itself against the slow pull of decay. It grows, it responds to the world around it, and, in nearly every case we know, it makes more of itself, passing along some kind of instructions, so that the pattern continues after the original has gone. On Earth, those instructions are written in long molecules of DNA, a code so old that it links a mushroom in a forest to a whale in the ocean to the person lying right now listening to this sentence. But when we look outward, we cannot assume that life elsewhere would use the same code or even the same kind of chemistry. So instead of searching for life directly, which we cannot yet do across such distances, scientists search for what are called biosignatures. A biosignature is a trace, a fingerprint, a whisper left behind by biology. It might be a gas in an atmosphere that living things produce and non-living processes struggle to explain. It might be a chemical imbalance so strange, so far from equilibrium, that the simplest explanation is something out there is actively working to maintain it. It might be a mineral formation that, on Earth, only forms with the help of microbes. The search for alien life, then, is really a search for these quiet signatures, scattered across moons and planets and the atmospheres of distant worlds, each one a small clue in an investigation that has been running for longer than most people realize. This search did not begin with rockets. It began with human beings lying on their backs, much like you are now looking up and wondering whether the lights above them were only lights or whether some of them were hearths warming other lives on other shores. The ancient philosopher Epicurus wrote, more than 2,000 years ago, that there must be infinite worlds, some like ours and some unlike it, because the universe was too vast and too generous to have made only one. For most of history, that was only a beautiful guess, offered into the dark with nothing to test it against. Then, in the 20th century, everything changed. Telescopes grew large enough to resolve the clouds of Venus and the deserts of Mars. Spacecraft learned to leave Earth's gravity and travel to other worlds directly. And in 1961, an astronomer named Frank Drake gathered a small group of scientists together and wrote an equation on a chalkboard. An equation meant not to give an answer, but to organize the question properly, breaking it into pieces, the rate of star formation, the fraction of stars with planets, the fraction of those planets that might host life, so that for the first time the search for life elsewhere could be approached the way science approaches anything, patiently, piece by piece. Carl Sagan, who would later become the most gentle and persistent voice for this search, once said that somewhere, something incredible is waiting to be known. He was not being dramatic. He was describing a simple mathematical truth, that in a universe with hundreds of billions of galaxies, each containing hundreds of billions of stars, the raw number of possible homes for life is almost too large to hold in a human mind. And so the search began in earnest, first with radio telescopes listening for signals, and later with something far more patient, the slow chemical detective work of looking for biosignatures on worlds we could actually visit or observe up close. Before we travel outward, it helps to remember how far life on our own planet has already proven willing to reach. For most of human history, we imagined life as a fragile thing, needing warmth, sunlight, and gentle conditions to survive at all. Then scientists began finding it in places that should, by every old assumption, have been empty. They found microbes living inside solid rock more than a mile beneath the surface, in complete darkness, subsisting on nothing but the faint chemical energy locked inside minerals. They found bacteria living happily in boiling volcanic springs, in water so acidic it would dissolve metal, and in Antarctic lakes sealed beneath thousands of feet of ice for millions of years, cut off entirely from sunlight and from the open air. They found tiny, eight-legged creatures called tardigrades that can survive being frozen to near absolute zero, boiled far past the point where most life would die, dried out completely until their bodies become little more than dust, and even exposed directly to the vacuum of space, only to rehydrate later and continue on quietly, as though nothing unusual had happened at all. Each of these discoveries did the same gentle work. It moved the boundary of what we consider possible for life a little further outward, a little further into the dark, a little further into the cold, a little further away from anything resembling comfort. If life on Earth could be this stubborn, this creative, this willing to take hold in places we once thought entirely hostile to it, then perhaps the same stubbornness exists on other worlds too, waiting quietly in conditions we have only just begun to consider survivable. Let's rest here in this history for a moment. Let it settle, the way starlight settles onto still water, slow and without urgency. The first real test of this new kind of search happened not among the stars, but on the dusty red plains of Mars. In 1976, two spacecraft named Viking 1 and Viking 2 landed gently on the Martian surface, carrying with them a set of small, careful experiments designed to answer one question: is there something alive in this soil? One of those experiments was called the labeled release experiment. Scientists took a sample of Martian soil, added a nutrient broth labeled with a special kind of carbon, and watched to see whether anything in the soil would consume it and release gas, the way living things on Earth do when they eat. And something happened. Gas was released quickly and in a pattern that on Earth would have been a clear signature of biological activity. For a brief and extraordinary moment, some of the scientists involved believed they might have found the first proof of life beyond Earth. But then a companion experiment, designed to detect organic molecules directly, found none. And the excitement cooled into decades of careful, unresolved debate. Some chemists later proposed that strange, oxidizing compounds in the Martian soil, without any life at all, could explain the gas release. Others, including one of the original mission scientists, spent the rest of his long career arguing that the simplest explanation was still the first one, that something in that red soil had, however, briefly breathed. To this day, the Viking-labeled release results have never been fully and universally explained. It remains one of the strangest open questions in planetary science, a small, patient mystery from 1976 that modern missions to Mars are still in their own way trying to close. While that question sat unresolved, a second piece of evidence arrived, and it did not come from Mars at all but from Antarctica. In 1984, scientists found a blackened, potato-sized meteorite lying on the ice, and later chemical analysis revealed it had been blasted off the surface of Mars by an ancient impact, drifted through space for millions of years, and eventually fallen to Earth. It was named ALH 84001 after the Allen Hills region where it was discovered. In 1996, a team of NASA scientists announced something remarkable. Inside this Martian rock, they had found tiny structures, smaller than a human red blood cell, that resembled fossilized bacteria. They had also found carbonate minerals and specific chemical compounds that together seemed to suggest ancient biological activity on Mars itself, billions of years in the past. For a short time, it was front-page news around the world, and even the President of the United States addressed the country about it, calling it one of the most stunning insights into our universe that science had ever uncovered. The scientific community, as it should, responded with rigorous and sometimes fierce scrutiny. Other researchers argued that the tiny structures were far too small to be true fossilized, cells that the carbonates could have formed through purely geological processes, and that the organic compounds detected might simply be contamination from Antarctic ice. The debate over ALH 84001 has never fully closed. It sits today in a strange and honest scientific limbo, neither proven nor disproven, a reminder that the search for life is rarely a single dramatic discovery, and far more often a slow, careful argument that lasts for decades, conducted by people who have devoted entire careers to getting it right, rather than getting it fast. Rest for a moment in that patience. There is something deeply calming in it, if you let yourself feel it, the idea that some questions are allowed to remain open for a very long time, held gently, without needing to be resolved before you can sleep. Mars offered one more quiet clue decades later, drifting not in ancient rock but in its thin, cold air. In 2003 and again in the years that followed, telescopes on Earth and instruments orbiting Mars detected faint traces of methane in the Martian atmosphere, appearing in small plumes that seemed to rise and fade with the seasons. On Earth, most of the methane in our air comes from living things, from the digestion of countless microbes, from wetlands, from the slow breath of the biosphere itself. Methane does not last long in an atmosphere, broken down steadily by sunlight, which means that if it is being detected at all, something on Mars must be actively replenishing it, again and again, season after season. In 2019, the Curiosity rover, sitting quietly inside an ancient crater called Gale, detected its own localized spike in methane directly from the Martian surface, a reading so unexpected that mission scientists spent days simply checking and rechecking their instruments before trusting it. Geological explanations remain entirely possible. Methane can be produced by certain reactions between rock and water, with no biology involved at all, and Mars may simply be releasing ancient methane trapped in its crust for billions of years. But the honest truth is that nobody yet knows for certain which explanation is correct, and that uncertainty itself is a kind of evidence, a small red planet quietly exhaling something that we cannot yet fully account for. While Mars kept its old secrets close, something else was happening much closer to home. On our own planet, in places nobody had thought to look. In 1977, scientists exploring the deep ocean floor near the Galapagos Islands, using a small submersible, found something that should not have existed according to the biology of the time. Around cracks in the seafloor called hydrothermal vents, where mineral-rich water, superheated by the Earth's interior, poured out into the crushing dark of the deep ocean, they found entire ecosystems thriving. Tube worms taller than a person, blind white crabs, dense colonies of bacteria, all living without a single ray of sunlight, all built instead on a foundation of chemistry, drawing their energy not from the sun, but from the chemical reactions between the vent fluid and the surrounding seawater. This discovery quietly rewrote the boundaries of where life could exist. For the first time, scientists understood that sunlight was not a requirement for life, only one possible energy source among others, and once that boundary fell, an entirely new category of worlds opened up for consideration. Worlds with no sunlight at all, worlds hidden beneath miles of ice, worlds that had been dismissed as lifeless simply because they were dark. This is where our story returns to that small moon we began with tonight, drifting quietly in the outer solar system. Its name is Enceladus, a moon of Saturn only slightly larger than the length of England, so small that early astronomers assumed it could hold no interior warmth at all, nothing but ancient, frozen, inert ice. Then in 2005, the Cassini spacecraft flew past Enceladus and found something nobody expected. Enormous plumes of water vapor and ice crystals erupting from cracks near its south pole, spraying hundreds of miles into space. Cassini turned back, deliberately, and flew directly through one of these plumes, tasting the material as it passed. What it found was extraordinary. Water, salts very similar to Earth's oceans, organic molecules, and most tellingly of all, molecular hydrogen. On Earth, molecular hydrogen near hydrothermal vents is exactly the kind of chemical energy that deep-sea microbes use to survive without sunlight, the very same chemistry first discovered near the Galapagos vents decades earlier. Its presence in the plumes of Enceladus suggested that similar hydrothermal activity might be occurring on the seafloor of its hidden ocean, chemistry that, on Earth, feeds entire ecosystems in total darkness. Scientists were careful, as they always are, to say that this was not proof of life, only proof that the ingredients and the energy source that life uses here on Earth also exist there, in that hidden sea right now, while you are lying here listening to this sentence. Let that settle for a moment. Somewhere above you, in the true present tense, not in some ancient fossil record but happening right now, an ocean older than the dinosaurs is quietly churning beneath a shell of ice, warmed by hidden hydrothermal vents, breathing hydrogen into space through cracks that catch the sunlight of a star nearly 1 billion miles away. Enceladus is not alone in this. Around Jupiter, a larger moon named Europa holds what may be the largest ocean in the solar system, twice the volume of all of Earth's oceans combined, sealed beneath an icy crust, and kept warm by the same kind of gravitational flexing that heats Enceladus. The gentle, relentless tug of Jupiter's immense gravity, squeezing and releasing the moon's interior as it orbits, generating heat the way bending a metal wire back and forth generates warmth in your hands. The Hubble Space Telescope has observed what may be plume activity on Europa as well, faint and inconsistent, but tantalizing. And in the coming years, a spacecraft named Europa Clipper, already on its way, will fly close to that moon again and again, mapping its ice, measuring its ocean, and searching for exactly the kind of chemical signatures that might tell us whether that vast hidden sea could support life, or perhaps quietly already does. We are in our own lifetimes watching the search for alien life move from philosophy into direct exploration, one careful flyby at a time. Not far from Enceladus, orbiting the same ringed planet, there is a moon so strange that scientists have described it as the closest thing in our solar system to a preserved frozen memory of early Earth. Its name is Titan, and it is the only other place we know of anywhere in the universe, with stable liquid on its surface, rivers, lakes, and even rain, falling from a thick orange sky. But the liquid on Titan is not water. It is far too cold for that, nearly 300 degrees below zero. Cold enough that water freezes into rock-hard ice. Instead, Titan's rivers and lakes are filled with liquid methane and ethane, the same molecules that here on Earth we know mostly as fuel. Beneath that frozen surface, Titan is also believed to hide a deep, hidden ocean of liquid water mixed with ammonia, kept warm by the same gentle gravitational flexing that warms Enceladus and Europa. Some scientists have wondered whether life could exist, not in that hidden water ocean, but in the strange methane lakes above it, using an entirely different chemistry than anything found on Earth, a form of biology so unfamiliar that we might not recognize it even if we were looking directly at it. A spacecraft named Dragonfly, a small nuclear-powered helicopter, is already being built to fly across Titan's orange skies in the coming years, landing again and again at different sites, testing the chemistry of this strange moon directly, searching for the kind of complex organic molecules that might be taking their very first slow steps towards something we would recognize as living. Let's drift now toward a different kind of world, closer to the Sun, where the evidence takes their very different and much stranger shape. Venus is, in almost every way, Earth's discouraging twin, similar in size, similar in the materials from which it formed, and yet its surface today is hot enough to melt lead, its atmosphere a crushing weight of carbon dioxide, its skies filled with clouds of sulfuric acid. It is, by every reasonable measure, one of the most hostile places in the solar system. And yet, high above that hellish surface, at an altitude where the temperature and pressure become surprisingly similar to a mild day here on Earth, something strange has been detected in the clouds. In 2020, a team of astronomers announced they had found a gas called phosphine in the atmosphere of Venus, in concentrations that were difficult to explain through any known non-biological process. On Earth, phosphine is produced almost exclusively by living organisms, or by human industry, deep in oxygen-starved environments like swamps, wetlands, and the guts of certain animals. Finding it drifting in the clouds of Venus, a planet with no oxygen-poor swamps, no known industry, sent a quiet shockwave through the scientific community. Could there be microbial life drifting in the temperate cloud layer of Venus, using some chemistry we do not yet fully understand, producing phosphine as a kind of exhaled breath, the way certain microbes do here on Earth? The response, as good science always requires, was immediate and careful scrutiny. Other teams re-examined the data and raised serious questions about whether the phosphine signal was as strong as first reported, some finding much weaker evidence, others questioning the calibration of the telescope data itself. Additional studies proposed that unusual volcanic activity or unknown atmospheric chemistry might explain phosphine without any biology involved at all. The debate over Venus phosphine remains unresolved today, a genuinely open scientific question. Neither confirmed nor dismissed, and for that reason it stands as one of the most fascinating live mysteries in modern astrobiology, a mystery that new missions, planned to fly directly through the Venusian clouds in the coming years, are specifically designed to help resolve. There is something worth noticing quietly in how science moves through moments like this. It does not rush to declare a discovery. It sits with uncertainty. It gathers more data slowly, patiently, the way you might turn a stone over gently in your palm rather than throwing it before you have really looked at it. That same patience and that same careful excitement brings us now to the most recent, and in many ways the most compelling piece of evidence in our entire journey tonight. And it comes not from within our own solar system, but from a small planet circling a star nearly 40 light-years away. Let yourself drift there slowly. 40 light-years is a distance that the fastest spacecraft humans have ever built would take tens of thousands of years to cross. And yet light itself, patient and tireless, makes the journey easily, carrying with it, faintly, the chemical fingerprint of a distant planet's atmosphere. The planet is called K2-18b, and it orbits a small cool star in the constellation Leo. It is considerably larger than Earth, roughly 8.5 times its mass, and it orbits within what astronomers call the habitable zone, the narrow, precious band of distance from a star where temperatures might allow liquid water to exist on a planet's surface, neither so close that oceans boil away, nor so far that they freeze solid. Some scientists believe K2-18b may belong to a category of worlds sometimes called a Hycean planet, a word built from hydrogen and ocean, describing a planet with a thick hydrogen atmosphere sitting above a vast, warm global ocean, an entire world wrapped in water beneath a hazy sky. In 2023, and again with greater confidence in 2025, astronomers using the James Webb Space Telescope, humanity's largest and most sensitive eye ever pointed at the sky, studied the light passing through K2-18b's atmosphere as the planet crossed in front of its star. As that starlight filtered through the planet's air, certain wavelengths were absorbed by the molecules present, leaving a kind of chemical shadow, a fingerprint embedded in the light that eventually reached Earth. Within that fingerprint, scientists found signs of dimethyl sulfide and a related compound called dimethyl disulfide. Here on Earth, these are gases produced overwhelmingly, almost exclusively, by living organisms, particularly marine phytoplankton, the microscopic ocean life that quietly perfumes the sea air you might breathe while standing on a beach. We do not know of any significant non-biological process that produces these gases in large quantities, either on Earth or in laboratory experiments, attempting to simulate other worlds. If confirmed, and the researchers themselves have been careful, appropriately careful, to stress that confirmation requires more observation. This would represent the strongest hint yet detected of a possible biological process occurring on a planet outside our solar system. The lead scientist on this research described the moment of seeing the data not with shouting excitement, but with quiet, careful astonishment, the feeling of standing at the very edge of what humanity has ever been able to know. Let this settle into you slowly, the way warmth settles into cold hands held near a fire. 40 light-years away, a planet drifts around its star, wrapped in clouds, its air carrying a chemical whisper that, if it means what it might mean, would suggest that somewhere beneath that hazy sky, an ocean is alive with something small and green and endlessly patient, breathing gently into the atmosphere above it, the same way plankton breathe into the air above our own blue seas. We do not know yet. That not knowing is not a disappointment. It is an invitation, the universe leaving its door only slightly open, enough to make us lean closer, not enough to answer everything at once. K2-18b is not the only distant world holding our attention tonight. Not far away in cosmic terms, only about 40 light-years in another direction, a small dim red star called TRAPPIST-1 holds 7 rocky planets in careful orbit, tucked in so closely together that if you stood on the surface of one, the others would appear in the sky not as distant points of light, but as visible disks. Some larger than our own moon appears from Earth, drifting slowly overhead. At least 3 of these 7 worlds sit within a zone where liquid water could plausibly exist. The James Webb Space Telescope has already begun studying their atmospheres, one careful transit at a time. And while no clear biosignature has yet been found there, scientists continue to watch closely, because a single star system holding this many potentially habitable worlds is, statistically, an extraordinary gift. 7 separate chances for the same quiet question to be answered. There is a reason this uncertainty feels less like frustration and more like wonder, and it has to do with something called the Fermi Paradox, named for the physicist Enrico Fermi, who once, over lunch with colleagues in 1950, asked a simple and now famous question. If the universe is so vast and so old and so filled with stars and planets, then where is everyone? Why, if life should statistically be common, have we not yet found clear, undeniable proof of it? Scientists have proposed many gentle answers to this question over the decades. Perhaps life is common, but intelligent. Technological life is rare, a much narrower filter than simple biology. Perhaps civilizations tend not to last very long, cosmically speaking, and the timing of two. Civilizations existing close enough in space and time to notice each other is itself extraordinarily unlikely. Perhaps the distances involved are simply so vast, so genuinely immense, that even if the galaxy is quietly full of life, most of it will simply never cross paths with any other, each civilization living out its entire existence within its own small, unnoticed pocket of the dark. Or perhaps, and this is the possibility our journey tonight leans toward, we have simply not yet learned how to listen and look in the right way, and the evidence has been patiently accumulating all along, in ice plumes and Martian soil and the clouds of distant planets, waiting for us to become careful enough and patient enough to recognize it. In 1977, a radio telescope in Ohio recorded an unusually strong narrowband signal from the direction of the constellation Sagittarius, a signal so striking that the astronomer reviewing the data circled it on the printout and wrote in the margin the now famous word, "Wow." The wow signal, as it came to be known, lasted only 72 seconds, matched no known natural source, and despite decades of careful searching has never been detected again. It remains to this day unexplained, neither confirmed as artificial nor fully identified as natural, a single, brief, beautiful mystery from the summer of 1977 that still occupies a quiet corner of every radio astronomer's imagination. Since then, projects like the Search for Extraterrestrial Intelligence and its modern successor Breakthrough Listen have spent decades quietly scanning millions of stars for any repeat of that signal or anything like it, patiently, methodically, without ever losing hope and without ever needing to rush. Before we let this journey settle fully into rest, it helps to hold gently just how large the search itself really is. Our galaxy alone, the Milky Way, contains somewhere between 100 and 400 billion stars, a number so large that if you tried to count them one by one, at a rate of 1 star each second, it would take you longer than the current age of the universe, simply to finish counting. And the Milky Way is only one galaxy, among an estimated 2 trillion others, scattered across the observable universe, each one its own vast island of stars, many of them holding planets of their own, planets we are only now beginning to learn how to see at all. We have, as a species, confirmed the existence of more than 5,000 planets around. Other stars, almost all of them discovered only in the last 30 years, a blink of an eye compared to how long humans have been looking up and wondering. And every single one of those 5,000 worlds was found before we had even finished exploring the handful of moons and planets in our own small solar system. The very places where Enceladus and Europa and Mars and Titan and Venus still hold their oldest, quietest secrets. Given numbers this large, it becomes strange, almost improbable, to imagine that Earth alone, among all of it, learned the trick of being alive. Not impossible, simply strange in the way that finding a single grain of colored sand on an endless beach and assuming it must be the only one would be strange. This is not proof of anything. It is only scale laid out gently in front of you, the kind of scale that makes searching feel not desperate, but patient, the quiet, reasonable work of a species that has finally built instruments sensitive enough to start answering a question it has asked since before it had language for it at all. Let's slow down now together, the way the night itself slows down in its deepest hours. We have traveled a long way tonight, from a cracked, icy moon breathing hydrogen into space to a red desert where 2 small spacecraft once asked simple questions of ancient soil to a blackened meteorite carrying possible fossils, across millions of years and millions of miles, to the scalding clouds of Venus holding a stubborn, unresolved mystery, to a hazy blue world 40 light years distant, carrying in its air a chemical perfume that smells faintly of living oceans. None of this, taken individually, is final proof. Each piece is a fragment, a whisper, a clue left behind, the way a single set of footprints in fresh snow does not prove who walked there, but is enough to make you look up and wonder and feel your heart soften with the possibility. And perhaps that is exactly the right way to hold this search, not as a race toward a single dramatic answer, but as a long, patient act of listening, generation after generation, telescope after telescope, spacecraft after spacecraft, each one adding one more faint thread to a tapestry too large for any single lifetime to finish weaving. Carl Sagan once wrote that we are a way for the universe to know itself, that the atoms in our bodies were forged in the hearts of ancient stars, scattered across space when those stars died and gathered again slowly into planets and oceans, and eventually into people quiet enough and curious enough to look up and ask whether anyone else out there is asking the same questions. If it turns out that Enceladus is truly alive, hidden beneath its ice, or that K2-18b's ocean truly breathes, or that some ancient Martian soil once truly stirred with something that could be called living, it will not diminish the wonder of our own existence here on Earth. It will only widen it, the way a single candle does not lose its light by lighting another. Let yourself imagine gently what it might feel like to wake up one morning in a world that finally knows for certain it is not alone in this way, not through fear, not through invasion or arrival, but through the quiet, patient confirmation of a single gas in a distant atmosphere, a single microbe in an ancient rock, a single plume of ice caught rising silently into starlight. It would not need to be loud. It might arrive the way most important truths arrive, quietly in a research paper, read late at night by a handful of tired, careful scientists who look at each other across a lab and simply nod, because the data finally, gently, agrees with itself. And somewhere very far above you now, that same small icy moon is still turning slowly in, the dark, its plumes still rising, catching starlight, falling back down as snow onto an ocean that has been waiting patiently, far longer than any of us have been alive to wonder about it. You do not need to solve this tonight. You only needed to come along and see how far the evidence has already carried us, and let the rest settle into the quiet, unfinished, hopeful place where all of the best questions are allowed to rest. The clouds of Venus continue turning overhead, somewhere in the solar system's morning light, unresolved, unhurried, waiting for the next spacecraft to ask them, gently once again, whether they are hiding something alive. Mars keeps its red silence, its ancient meteorite still sitting in a laboratory drawer, undecided, patient, in no rush to give up its secret. And 40 light-years away, past more stars than you could ever count from where you are lying now, a hazy blue world drifts quietly around its star, its atmosphere carrying whatever truth it carries, waiting patiently for the next careful measurement, the next long exposure, the next quiet moment when a scientist leans forward at a screen and whispers, "There it is again." Let your breathing follow that same patience now. Slow, unhurried, certain of nothing, and yet comforted by everything we have gathered so far. Somewhere out there in the deep and generous dark, something extraordinary may already be alive, breathing its own quiet breath into its own quiet sky, utterly unaware that on a small blue world, 40 light-years away, someone lying very still, eyes closed, is only just now learning how to listen for it. Rest now. The universe is not going anywhere. It will still be there, turning gently, patient and vast and quietly alive with possibility, when you wake. For now, let it hold you, the way it has always held everything, gently and without end. Think, if you like, of all the people across history who have lain beneath this same wide sky, wondering the same soft wondering long before telescopes, long before spacecraft, long before anyone had a single piece of real evidence to hold on to. They had only the stars themselves and their own quiet imaginations, and still they wondered, and still they hoped, and still they found comfort in simply asking the question out loud into the dark. You are luckier than they were in a small and gentle way. You get to fall asleep tonight knowing that somewhere an icy moon is breathing hydrogen into space, that somewhere a red planet is exhaling a gas we cannot fully explain, that somewhere, 40 light-years distant, an atmosphere carries the faint chemical perfume of what might be a living sea. You do not need answers to feel comforted by that. You only need the knowing that the question is, at last, being asked in exactly the right way, patiently, carefully, by people who have devoted their lives to listening closely enough to hear the universe's quietest whispers. Let your own thoughts grow quiet now too, the way a radio telescope after a long night of listening is gently powered down, its dish turned toward the horizon, resting until the stars rise again. There will be more evidence tomorrow, and next year, and next decade, arriving slowly, the way it always has, one careful measurement at a time. Tonight there is only this, the vast dark, the small blue world you are lying on, and the quiet, patient certainty that somewhere out there the universe is still unfolding, still breathing, still, perhaps, gently alive. Sleep now. It will all still be here when you wake, turning softly, endlessly, and waiting.